Okay, well, good afternoon. Welcome to lecture 6 of Physics 2820. And today I want to talk about, this is our last lecture on projectile motion. Specifically, I want to make these objects we're sending spin in the air. So here's the idea. What we're going to do is go through a Jupyter Notebook as we has been, start by importing in some basic libraries that we need. And the idea is, rather than looking at projectiles that are going to cause damage, like cannon shells, let's consider something a little more friendly, like baseball. And the idea here is we're going to write some models to understand the dynamics of a spinning thrown baseball. Air drag, again, of course, is important in any real projectile motion. And what I want to remind you of what we discussed last week was the idea of air drag is that air drag is a force. Force is equal to mass times acceleration. So the acceleration that's due to the drag, the force per unit mass, what we can do is we can write that as a bunch of terms, which is proportional to the velocity squared. As we talked about, this is one way of modeling air drag. That is the density of the air, some proportionality constant, a cross-sectional area, and then you, of course, got the speed. And the idea of air drag is the drag force is dependent on the velocity squared. So the faster something moves, there's more air drag. If there's no velocity at all, if an object isn't moving, there is no air drag. We either can talk about it in terms of all of these coefficients, and that has to do with the geometry of the object and the material it's flowing, going through, or you could just take all of the constants, that is, all of these things right here, and you could wrap that all up into a single constant, and we're going to call that constant the drag coefficient. So it's a little bit of a confusion. There's two drag coefficients. There's a drag coefficient if you're thinking about the full explanation, or a drag coefficient that embeds everything about the behavior in there. The units are slightly different. Okay, so the thing about drag coefficients is when you actually go and do experiments, and this is really the only way of measuring what a drag coefficient is it turns out that beyond just its functional dependence of air drag being dependent on the speed squared, once you correct for that, it turns out that the drag coefficient itself, as in just this number right here, this coefficient is not a constant. It's dependent on how fast you're moving. So what you can do is you can do experiments, as in throw things or make things move in a wind tunnel, change the relative velocity, and measure the drag on the object. And one of the things you find is, depending upon the surface of that ball, you have different drag coefficients. Now, drag coefficients for slow-moving things are basically around a half. Depending on whether or not the ball is smooth, the ball is smooth or rough, that drag coefficient can change, and it can change with speed. The faster something moves, the drag coefficient tends to go down. But it turns out if the ball is rough, as in it's got abrasions or it's got some rough surface, then once it starts going sufficiently fast, the flow of air over the ball becomes turbulent, and that actually increases the drag coefficient again. So you get this interesting dynamical behavior. For baseballs, which are not perfectly smooth, but they're sort of smooth, but of course they've got the bump of the seam on them, the curve that we're interested in would be something of the shape of this guy right here. There's sort of theoretically. And whether or not you model that as a hyperbolic tangent or as some sort of exponential or inverse exponential relationship, one of the things we can do is we could look up an approximation or parameterization of how the drag force depends upon the speed. Now, again, this is the drag coefficient. The drag force is this value, CD, multiplied by the square of the speed. This is just indicating the fact that although the number is nominally around 0.004, there's this dependence on velocity. And particularly with these two parameters right here, this is a parameterization of it. So this is something you could look up in a book. In particular, I found this in some textbook on numerical methods and the physics of baseball. Okay, so with that, we could implement this drag coefficient in a function, so we could use it to model the dynamics of a baseball. So I could take this equation, the CD equals a bunch of stuff, and I could code it up in a function. And the idea of this is to embed this bit of mathematics inside some function. This is going to compute the baseball drag, and as I said, it's dependent upon the speed. It's a function that for any particular value of speed, here are the two constants that are given in the problem, it's going to evaluate this expression, and it's going to return that drag coefficient. The way of doing this is now we don't ever need to actually talk about this long and cumbersome equation. We can just refer to this as the baseball drag function and use that all the way through. Again, to create these funny sort of symbols, I'm using a Greek letter delta. I'm doing that because the equation had a Greek letter delta, so it makes sense to actually have a delta. And again, in the Jupyter environment, if you put in a backspace or a backslash, the Greek word you're trying to type, and then hit the tab key, that will typeset a character. Python understands and can use most of the Unicode character set for identifiers if you need to. That's just what this text down here says. So how does this work? If I run this piece of code and I have a function, so now the baseball drag at 30 meters per second is given by 0.001. The nice thing about using NumPy, and you see I'm using NumPy here, is NumPy works for not only single values, but also arrays of values or lists of values. What that means is if I have a whole list or an array of velocities, say 20, 30, 40, 50, and I pass that into a function, because I'm using NumPy operators, that means that I'll evaluate this function at every single point in the list. So I'll add one more line to make this concrete. The array V is 20, 30, 40, 50. And because we're using NumPy, it's going to evaluate it for us for the first thing, the second thing, the third thing, and the fourth thing. In other programming languages, you might need to do a loop to go through these things. Python has this functionality built in. Any language that has this kind of functionality is sort of a vector-based language. Fortran has this, MATLAB has this, other languages have this kind of functionality. But it lets us fairly quickly evaluate things without having to worry about loops. In general, use NumPy when we're doing this course. There is another library called Math. I wouldn't ever use it, just use NumPy because it gives you this additional functionality. Okay, let's make some plots, right? So let's make an array of different values of speed. So 20 meters per second, 21, 22, 23, 24, all the way up to 59. Range goes up to, but not including 60. Let's give ourselves a window to draw something in and plot how this drag coefficient depends upon the speed. Okay, and there we go. So there's sort of a characteristic shape. And my point is this graph, this plot, is supposed to be an analytical representation of, where is the tool? Of this curve right here. So it sort of drops down and comes back. That curve is being represented by that function. Now the scale is a bit different, but it's got that basic sort of shape all the way to it. The thing about this drag coefficient, and you can work through what the unit should be, a drag coefficient, as in the thing you're going to multiply v squared by, it's going to have units of per meters. So that means in terms of a force, to figure out the drag force, you take this drag coefficient, this value which is in per meters, and you multiply it by v squared, meters squared per second squared. That means drag coefficient times v squared has units of meters per second squared. It's an acceleration. So what we can do is take that acceleration, or that force per unit mass, which is what an acceleration is, and write down the drag force in terms of three components. Drag forces always oppose the velocity. So it doesn't matter what direction you're going, your drag force is always going to be pointed in the opposite direction of your velocity. And as we talked about last time, you can take a velocity vector and split it up into components so that the drag is going to be dependent upon both the magnitude of the velocity and then the component in that direction. This is really just v squared in the direction of the vx component, v squared in the direction of vy, v squared in the direction or the component in that direction with a minus sign all the way through. Now, whether or not you use a complicated formulation like I've given, where CD depends upon V, or you go, that's just too complicated for me. I just want a constant. If you look up a textbook by Adair on the physics of baseball, 6 is good. There was a comment in the chat going, why did I put this in here? That's completely optional. If I don't put it in there, it will draw in it for me. I just get in the habit of doing that because sometimes I often want to draw multiple plots. And that's just something that I commonly do. By default, you could just have a 1-by-1 plot. As I said, if you don't put it in there, Python will create a figure for you automatically. So it's an optional thing, but needed if you want to do multiple subplots. Okay, so drag we talked about. I want to introduce a new piece of dynamics. I want to talk about spin. The idea here is I want to investigate how a spinning object changes the projectile motion of a projectile. What's this called? The effect of it. It's not air drag. This is something that's typically called the Magnus effect or the Magnus force. And I think the best way of going through this is to actually go with a little video that I found. I don't know if anyone out there ever watches the production Veritasium, but these are little YouTube clips. And I think this guy does a very good job of explaining this. And so hopefully, if the sound is working, I'm going to try and do that now. Okay then, so that was a nice little description, I think, of this effect called the Magnus force. And it has to do with spinning objects. What I would like to do is take that video, take that little bit of thinking, and see if we can apply a Magnus effect into a model of a projectile motion. The goal here is to figure out how to model a Magnus force so that it all works. Just before I go any further, there was a question that just popped up on the chat that said, is Lecture 6 available on Jupyter Hub? Yes, it definitely is. If you're not seeing it, you probably didn't log in through the link provided on the D2L page. So that kind of issue is something that Kyle in the room may want to address. If someone has a problem finding it, that's a good thing for you to flag Kyle down for. Okay, so Magnus force. The idea here is it has to do with the spin of an object. Just to recap what the video said. The idea is you've got air going over a ball. Because of friction between the surface of the ball and the air, the ball, if it's spinning in a clockwise direction, will tend to pull and drag that air and deflect it downwards, right? At the same token, the air going at the bottom of the ball gets slowed down a little bit more, so it doesn't get dragged up, it gets stopped, it deflects everything. Now, the details of why there is a magnet force, take a course in fluid dynamics. That'd be beyond the scope of this course to really understand it, but we can do a little bit of understanding why this would be true. This is a spinning object, okay? It's a spinning object. It means it has angular velocity. That means that the velocity at the very top of this thing and the velocity at the very bottom are going to be slightly different. What do I mean by slightly different? Well, there's angular velocity, the rate at which this is spinning around, and then there's the speed at which the object as a whole is moving, right? So the arrow indicates the center of mass of the ball is moving towards the right. Because the thing is moving backwards, on this side, the velocity relative to the air of this side is a little bit, I want to make sure I get the arrows correct here. Yeah, it's a little bit slower, and on this side, it's a little bit faster. So center of mass of the ball is moving at a certain speed, but the two edges are moving at slightly different speeds because it's also spinning around. If you consider those effects, you can realize that this force, this magnet force, is going to be dependent upon the difference between the speed at the top and the speed at the bottom.
No.
And so what you can do is you can say V plus R omega
What?
and V minus R omega, and you get the difference between those two things.
I think it is. Your rose gold.
So the Magnus force is going to be proportional to the difference between those two terms. If you write that out, that is a speed at the top and the speed at the bottom and a difference, and you expand out all of these terms, and these are one of the things you could do just by doing the algebra, what you'll find is the dominant term the term that's the most significant in size, is proportional to the radius of the ball, the speed of the ball, and the angular velocity of the ball. What that means is in terms of a proportionality constant.
Man, I'm so nervous he's going to talk about my assignment.
I don't think he's going to talk about your assignment.
It's up on the screen.
Yeah, he could just be correcting it.
So Andrew, your mic's not muted, so I'm not going to talk about your assignment. I was gonna defer to that, but you just got to draw attention to it. No problem at all. I'm glad the mics work. No problem at all, guys. I'm not going to talk about anyone's assignment in particular. Don't worry about that. What I want to do is I want to talk about the dependence of the Magnus force as a function of the speed it's moving and the angular velocity. What we're really saying is the Magnus force, this force that we're interested in, is dependent upon the product of an angular velocity and a velocity. So if it's moving in the horizontal direction, the x direction, the Magnus force is going to scale proportional to how fast it's moving and how fast it is moving. How fast it is rotating. I should make that more clear. Okay, so you bring those all things together, and what we have is, if you do this in the fully general 3D case, because of course it doesn't need to spin only in a clockwise direction, it could also spin in a direction perpendicular to the axis, or if it's moving in this direction, it could spin in this direction as well, going all the way around. It could spin in any one of three directions. And if you do the analysis in all three directions, what you find is Magnus force is proportional to the cross product between an angular velocity and a velocity. Okay, so cross products. If you remember doing this from first year physics, from Physics 1051, the idea is to think about the cross product of two vectors will give you a vector in the third direction. So in particular, if you imagine this object, it is spinning around, the axis of rotation is sticking into the page, right? If you remember using your right-hand rule, you can imagine putting an axis right here, and this is sticking into the page in the sense of the rotation is in this way. If you do the cross product between a vector into the page and a vector which represents the velocity to this direction, so do your right-handed rule, and I invite you to stick out a hand into the air to play with this. If you imagine a force which is going in, a vector which is into the page, and a vector which is to the left, then right-hand rule says there's going to be a force upwards all the way through, and that's your Magnus force. So apply right-hand rule, and you'll see this. And it works if it's spinning in any direction or any orientation. Again, what we can do is we can go to experiment and we can look up what a typical value of the coefficient is. So for a Magnus effect, that same textbook that told us about the drag on a baseball quotes that for a ball going at a typical velocity of a ball that has a typical mass of about 150 grams, this drag, this Magnus coefficient is about 4 times 10 to the minus 4. Again, rather than trying to understand all of the fluid mechanics of where this comes from, a little experiment is easy. Imagine you have a cylinder or a ball and air is going past the ball. What these are is little tracers, pieces of smoke basically, which is showing you the air. The cylinder starts by not spinning, and then the cylinder begins to spin. It spins in the sense of rotating in a clockwise direction that pulls the air around the back of it, deflecting the air upwards. There's a force of the cylinder or the ball on the air. So by Newton's third law, there's an equal and opposite force pushing downwards. That's the Magnus force. And that's what we want to model all the way through. To add the effect of the Magnus force into a numerical solution, what we want to recognize is now we're dealing with an equation of motion, which looks like this. Now, this is not supposed to be super scary, right? It's got a lot of things going on, but we already recognize what this really is. All we're dealing with here is the equation F equals ma. That's all it is. It's Newton's law. Of course, things are vectors. I'm putting the mass on this side. I'm getting rid of it here. And then I'm writing out all of the different forces that are acting on it divided by their mass. Well, force of gravity, mg, divided by the m. This is the force of gravity. This is the force of the drag. And this is the force of the Magnus force. So we split these things up into 3 different forces. That's what we want to model. This is our equation of motion. The next step, once we've written down the equation of motion, is to split it into components. This is a second order differential equation. Remember that acceleration is the second derivative of position. So what we do is we first split up the positions into derivatives called their velocities. We introduce this thing called v, velocity. And then we've got these 3 terms are the rate of change of velocity in the x, y, and z direction, where I've taken the z direction to indicate upwards against gravity, which is why gravity only appears in those bottom equations. These things, the y, z minus zy, vx, xy, this is just the components of when you do a cross product. Not that you need to know how to do a cross product. I've done it for you. Okay, so let's implement that code. Let's solve a model for projectile motion that includes both an air drag and a Magnus force. As we've been doing, the pattern of the template is I'm going to split my program into 2 parts. A part which is responsible for solving the numerical model, and a part which is responsible for plotting the results, and then some driver code or an application to pull it all together. So code with rotation. So I've taken a code which we've done before. We've looked at projectile motion. I'm going to call this thing a baseball stepper because it's going to step through time. It needs to take a bunch of parameters, not only an initial position, an initial velocity vector, but also something to do with its rate of rotation. The rate of rotation is a vector because the vector is the axis of rotation, and these are the amounts of rotation around the 3 things. So in terms of solving this problem, I'm going to have a bunch of initialization. All models are going to have something where it initializes the model. The model state is going to be given by the time, the position, and the velocity components. Every time I run my model, every time I loop through the model, I want to respond by saying what the state of the model is so I can retain it, measure it, plot it, visualize it. Models are going to end if a break condition is hit. Maybe I don't want to simulate it past a certain number of seconds, or maybe I want the ball to stop being simulated when it hits the ground. And I've got to implement the forces. Notice how I'm being very verbose in my coding. That's good style. It makes it very clear what you're doing. Rather than trying to have one massive line where you said Vx equals, and then try and put everything in one long line down here, what we can do is build it up into pieces. I have to talk about drag forces, so let's calculate the magnitude, calculate that drag coefficient, which might depend upon speed, figure out the components of drag. Then, let's calculate the Magnus force. Well, the Magnus force is just a constant times the cross product of the rate of velocity or angular velocity and the tangential or linear velocity in the 3 components. Let's calculate the force due to gravity. That's pretty easy. And put them together as the net force in the 3 components. This would allow me to add or remove even more forces if I wanted to model additional forces all the way through. Finally, there's the Euler algorithm. The idea of writing this system of differential equations, this guy right here, recognizing that if you replace each one of these derivatives with a finite difference, change of x over change of t, change of dvz over change of t, I can come up with a rule that lets me evaluate what these things will be at the next time step. That's the idea of Euler's model. Okay, so there's the first bit of code. I need an application to tie it all together. So something that's going to let me control this program. Let's set an initial position. Well, for a baseball, I don't know. If you're standing on a pitcher's mound, maybe you're about 2 meters off the ground. I need to set the initial velocity. Like we did before, maybe we want to handle the general case of throwing the ball at a certain angle with respect to the horizontal. I'm just going to go with 0, but the code's pretty easy. We know that cosine and sine depend upon radians. So let's convert that to a radian and have some initial pitch. Let's say I'm throwing this thing at 110 miles per hour. So a really good professional level baseball pitch. Let's figure out the components all the way through. And I'm going to simulate this model for up to 10 seconds. So even if I was to throw it very, very far, after 10 seconds, any ball that I throw, I'm expecting that will get back down to earth by any way of throwing it. Is this code needed? No, but it's good general code that I might need to reuse if I want to play with some parameters about it. This model is going to be set up. We're going to pass in all of those components into the stepper, and then we're going to iterate that stepper all the way through. Once we've done that, we're going to plot it. There was a question on the chat that said, why did I pass omega x, omega y, and omega z? Because those are the things I'm going to play with. I'm going to interact with this application to vary the amount of spin. I'm interested in how does spin affect the motion. Those are the parameters I want to vary. If you also wanted to look at how the initial angle or the initial speed, well, then you would add those in there as well. If you wanted to add more controls in your application, go ahead and add as many things as you like. I don't want to look at how initial speed and initial angle change the behavior. We looked at that already. I'm interested in how angular velocity, rotation, spin, adjust what's going on. Okay. And as before, we need some way of plotting the results. Now, we're getting into three-dimensional territory here. We've got a ball where you're throwing it. So if you throw it with, say, a curve ball, as you throw a curve ball, that ball is going to move both upwards and downwards, forward and back, and left and right. It's difficult to demonstrate what a three-dimensional motion will look like if you've only got a flat screen or a flat piece of paper. One way of achieving that is to draw multiple snapshots or multiple views of the motion. So here's the way that I'm going to solve this problem. I'm going to draw a function that takes all the information about the ball and makes three plots. And so the question was raised earlier, what's this plit.subplots thing? So here what I'm doing is I'm creating a 1x3 set of plots. I'm making this 16 units wide, 4 units tall. This is a handle to the figure as a whole. If you want to change some property of the figure, this is a list of all the axes all the way through. And rather than using plit.plot, what I'm going to use is this identifier to say the first axis, I want you to plot the x-coordinate as the horizontal and the z-coordinate as the vertical, set the labels. Let's put a line so it's really clear what the axes are, and I'm going to give it a title. And I'm going to say this is going to be my side view. Then I'm going to make another plot which plots the x-coordinate versus the y-coordinate. Those are the horizontal directions. It's going to be my top-down view. And then you could have a view from the perspective of looking at the picture, throwing the ball right at you. This would be a YZ view, a front view of what's going on. Okay, all of this is just to set up our program. These three basic pieces modified. We want to test it. What I'm going to do is write an interactive application where I'm going to vary the amount of spin involved so we can investigate what's going on. Okay, here's the basic plot. This is just good old-fashioned projectile motion. It initializes with no spin. So from its side view, you see a ball that's thrown at a height of 2 meters, launched at 50 miles an hour. It's going to go off to about 30, 31 meters before it hits the ground in nice projectile motion. From a top-down view, if you imagine looking at the path of this ball, looking down from the sky, well, the ball is going to go in a straight line. It's going to move in X, but it won't move left or right. And if you were to look at the ball coming straight at you, basically standing in front of the ball, what you would see is the ball coming from the top and going down to the bottom. And that's what you would see. What we want to do, though, is investigate what's going to go on. We learned in the video that if you apply top spin or back spin, that's going to change how this object proceeds. So in this coordinate system, X is in the direction that we're moving, Z is up, Y is the direction into the page, or the one that's at right angles to the motion. So if I make this thing spin into the page, what I want you to see is as I increase this number, so I'm making it spin faster and faster, the top-down view and the front view stay exactly the same. But look at the range. Before it was 30, now it's only 20. I'll go back to 0. So what's happening is if you give it top spin, the Magnus force is going to accelerate the object down. It's going to push it down faster. It's not going to go as far. The reverse is if you give an object backspin, so it's spinning around in a counterclockwise circle, then what's going to happen is the acceleration will be directed upwards. There'll be less acceleration downwards, net acceleration downwards. It'll travel further. Remember, in the unaccelerated case, it traveled distance of about 30 meters. If we give it backspin, this. Now, in the video, you saw this animation of them taking a light ball and really giving it a good spin, and it did a really interesting shape. So let's do that. Let's give it a lot of backspin. And you can see that if you give an object a lot of backspin, then you get this really interesting sort of set of dynamics. So what's happening is at every point along the model, you always have, and I'll draw on a ball. I'll draw on a ball. Here's my ball. Okay, hope everyone likes that nice ball. You're going to have a number of forces acting on this thing. You're going to have a force of gravity pulling in that direction. You're going to always have some amount of drag pointing in this direction. And then you've got your Magnus force. Well, at the very beginning, I'm going to draw a couple different circles here so we can make this really clear. When the motion's up here, okay, a bunch of arrows. We've got a force of gravity going downwards. Okay, that's not the right one. Undo. Arrows. You've got a force of gravity going this direction. You've got a velocity in this direction. And it's spinning, in a sense, into the page. And remember from right-hand rule, what that will mean is the Magnus force is going to be directed at right angles to the velocity and the orientation of the spin. Because there is a force acting in the upward direction, and when it's really spinning, the Magnus force is stronger than the acceleration due to gravity, that will start to accelerate it upwards. And so instead of curving down, it'll actually curve up. But at a later point in its trajectory, its velocity is now going in this direction. It's still spinning in a backspin sense with the axis of rotation into the board. That means that the Magnus force is at right angles to the velocity vector and the axis of spin. So now that's your Magnus force. And so what's interesting about this is your Magnus force is always changing all the way through. It's going up and up and up and up. And my guess is what's happening is as you're getting to the top here of the motion, it's spinning and spinning and spinning. I just need another symbol. When you're right at the top of this motion, I think what's going on, and we could look at the table, is you still have a force of gravity. But at this moment, you slowed right down to a complete stop. So you have basically no velocity in this direction. If you have no velocity in this direction, you have no drag, because drag is dependent upon the velocity. And if you've got no velocity, then you've got no Magnus force, right? So the Magnus force is changing based on the direction and the speed that you're moving. And so you'll get these interesting dynamics all the way through. Okay, clear all these drawings. So now we can go back and playing with this model one way or another way. Okay, but of course what we want to do is to do with the curveball. So imagine I'm playing baseball and I want to give this some side spin. I want to see what will happen as I deflect this thing one way or the other. in terms of a spinning ball that's oriented on its axis. So imagine the ball is moving in the increasing x direction. And what I want to do is I want to set it up so that it's spinning in this sense, as in spinning in this sort of sense. It's moving from left to right, but I'm giving it side spin. I'm going to throw a curveball. What that means is I want the spin to be in the direction of omega z. I want the axis of rotation to be in that sense. So if I do that, and I make it spin in one direction, can you see how from a side view, z and x is the same, but take a look what's happening from a top view. It's still going 30 meters towards the front, but now it's being deflected towards the left by about 2 meters. That's a lot of spin. We only want to give it a little bit of spin maybe. And you can see what happens is by the act of giving it some side spin, it's still moving, but from the point of view of, say, a batter trying to hit the ball is actually moving sideways towards the right. It only moves a few 5 or 6 centimeters inwards, but it is seen to be drifting. Likewise, if I give it spin in the other sense, so I'm spinning in the other direction, now the ball is going to be bending towards the right all the way through. Of course, I don't know how you would actually throw this, but you could also spin it along the axis of rotation. So you could spin it in the sense of like you throw a football, give it a spin in that axis, and that will contribute a small Magnus force. But if you look at the actual numbers, the value that's going on right here, 0.08, those are very small. And that's because the Magnus force depends upon the velocity, which is at right angles to the axis of rotation. If you throw something with spin, so the axis of rotation is in the direction you're throwing it, there's very little component to the velocity at a perpendicular axis. So you don't get much at all. So looking at these scales is sort of important all the way through. Okay, so before we move on, let me just check the chat, see what we got. Okay, Kayla, wait, how do you know that it is going to the left by 2 meters? Okay, I'm going to give it some side spin. And I'll show you what I'm seeing. This is the y direction, as in if it's moving from left to right, z is up, x is forward, y is left to right, in and out of the page. It's moving. As the ball moves from 0 to 30 meters in front of you, it's also being deflected by about 2 meters towards the left, or vice versa, 2 meters towards the right. Again, I'm getting the 2 meters by reading that off the graph. You also could see that same information from a front view. Here is a front view. This is the ball coming towards you. What path would it take? Well, it's still going down in the vertical, but it's moving towards your left, starting at 0 and ending up at 2 meters towards the left. So that's how I can see that it's moving 2 meters towards the left. Cassandra asked a question, said, can you explain the axis square brackets function? Okay. They're not functions, but what they are is allowing me to talk about these 3 different sets of axes. The normal behavior, and I'll go back to the example we had at the top, was if you want a single plot, if you don't do anything, you just get a plot. But if you want to talk about multiple plots, there is 8 plots in the vertical, 1 in the horizontal, or 1 plot in the horizontal, or 1 plot in the vertical and 8 along the horizontal, or any combination you want. What you're getting back here is a list. This thing is a list of all your different axes. You can tell something to be drawn in any one of those axes. So if I go back to the code, this plotting function, what it's doing is it creates a list of axes. And you always can print something else to figure out what it is. Show what it is. Can you see how this list, this AXS thing, is a list of 3 things? It is a matplot axis, comma, a matplotlib axis, comma, a matplotlib axis. It refers to this square, and this square. Plot, rectangle. What I can do is by talking about the first one or the second one or the third one, control which graph I want to talk about all the way through. They start at 0 because in Python we count starting at 0. We go 0, 1, 2. The first, the second, the third. And this is just a way of handling multiple plots inside of a graph. You don't need to do this. If this multiple graphs thing is just not working for you, an equivalent way of solving exactly the same code would be take this code and just make a single plot. Okay, no variation at all. And then you could just do plit.plot and plit.plot all the way through. And then make a new plot right here. To create a new plot. And then again, plit.plot, plit.plot. So two different ways of playing around with how to do multiple plots. You get a little more control if you leave it as axes all the way through. Okay. I'm just going to finish off this one more demonstration. This is three-dimensional motion. If you have been reading along in the textbook, this is a section in the textbook on spin. It talks about a 3D framework for drawing graphics. We're not doing the Open Physics 3D framework. We're not doing the Java, but I want to know, okay, well, this is a three-dimensional motion. How can I make this look three-dimensional? Well, Matplotlib supports three-dimensional drawing. The way of learning how to do this is you do a quick look in the Matplotlib example gallery, find something you like, and it turns out that all you need to do to make something 3D is import a 3D axis, and then when you're creating your figure, tell it that its projection is going to be 3D. This notation fig and axis is like making a single plot as opposed to a whole set of plots. Once I do that, what I'm able to do is plot things with 3 components, X, Y, and Z, all the way through. I'll show you what that looks like. So there is my projectile motion in X, Y, and Z. Let's give this ball a little bit of spin. Okay. Again, this blue trajectory in 3 dimensions is the projectile. It's moving in the X direction forward. It's moving downwards in Z, and it's being deflected towards the left. X equals 0, X equals Y. To sort of give it some sense on how to read this graph, this black line and this black line are the projections of that curve in the Z, Y plane and in the X, Y plane. Because maybe you want to look at that. To how do I draw these things on the edges? What we're doing is we're drawing just the X versus Y and keeping the third coordinate equal to 0. So X comma Y with Z always equal to 0, that draws this curve. So maybe that's a useful way of visualizing it. And there's lots of other ways of doing it. Now that we've got this tool, we can start having some fun with it. Maybe we want to give it backspin so that it does one of these neat sort of up things and say, well, what happens if I give it upspin and side spin? Okay, so now this is going to be the motion of the vector. It starts off at 2 meters up in the air. It's going to drift towards the left and raise up and then drop down. That'll be the projectile motion of what's going on here. If we really give it some interesting spin, maybe we'll spin it very, very far in the other direction. You can see that it moves up. It's moving up because of the backspin. It stops moving, but it still has spin. So as it starts to fall, it gets deflected towards the left. And as I play with these things, maybe I'll look at some extreme situations. You can get some interesting dynamics out of this thing. So here's a ball that goes up, around, and comes down. Here's one that, I don't know. I was playing around with these before. This is pretty cool. Okay, here's one that starts off at 2 meters. If you give it a really good spin in 2 directions and not spinning in another direction, that just means it's turning on some sort of axis. This thing will shoot up drift to the left, do a little loop-de-loop, and cross down. In profile, just looking at X and Y, it's that black shadow. In profile, just thinking about it in Z and X, it's doing this shape. Again, those three pictures are right here. This is what it looks like in side view, top-down view, and front view. The question was, is there a way to add one of those black lines to the Z plane? I saw that in the chat. Sure there is. What I want to do is I'd want to now plot X versus Y versus Z. Now what have I got? I've got X and Y. I've got Y and Z. I need X and Z. There we go. There's the third direction. Let's go back to that, another fun one. Okay, there we go. So you see the three shadows? I'm seeing it projected in the ZX direction, projected in the YX direction, and projected in the ZX direction. So the three shadows all the way through. So you can add in as many of these as you want, depending on what you're trying to visualize and you're trying to show. But again, where did this come from? How am I supposed to know how to do that? I'm going to remind you that we did talk about how to come up with examples. If I go to the reference on Matplotlib, there's all the documentation about it, but the best way of learning about these things is looking at the examples. Go and find an example that you're trying to recreate. I wanted to do something with 3D plotting. There's some 3D plots. I wanted to do a curve that was in space. I learned that it's called a parametric curve. I did that. And then I wanted to figure out how to draw it on the sides. So I looked at the different options and I saw this one right here and went, plot 2D data on a 3D plot. So there's an example of plotting dots with a curve. And there, buried in here, was an example, not that I can see it right. Oh, there it is. Of fixing one of the coordinates to be 0 and talking about it in a certain direction. So that's the idea, is you use the examples to come up with ways of plotting it. Maybe you want to do something where you're looking at surfaces. So here's a projection of the surfaces in the three directions. Again, use the gallery, use the examples as a way of figuring out what lines of code you need to modify, take existing code, and repurpose it to get it to work the way you want it to work. Okay, so we can play with things around. Before we continue on, so this is my last example of projectile motion. We're going to move away from Euler's method and start talking about more complicated dynamics in our next lecture. But we've seen this pattern now like 3 or 4 times where I've talked about a stepper, solving a model. I write down some equations all the way through, and then I tell you what it does. Is there any questions about the code that I've demonstrated in this lecture that we should talk about? And you're more than welcome to ask that question on a microphone if you've got it set up, if that's easier for you to do. And there is a microphone back where Kyle's sitting, because Kyle can say hello. Can you say hello, Kyle? Maybe he can't. Oh, he's smiling at me because he's just being put in the spot. Okay. Any other questions about this code base? Okay, let me finish this off then with another little video about applications of this Magnus effect.
Is your mic muted?
Is that better?
That's better.
That's better. Sorry, guys. I have to turn that on. Try this again. So what we've discovered is the path of these more complicated motions. If you have some physics you want to investigate, you can add that in by numerically solving for it. This is not the kind of motion that you can solve by pen and paper or blackboard and chalk, but it's something that we can very easily do once someone shows you a little bit of physics, like there's this thing called the Magnus effect. You can model a real world effect, like what would happen if you threw a basketball spinning off of the Gordon Dam. And we can get these things fairly quickly. In the chat, Cassandra asked the question, will we need to know any of the equations from the lecture? Well, yes, but no. Let me be clear. Do you need to know Newton's law? Yes, you absolutely need to know Newton's second law, F equals ma, required. Do you need to be able to understand a drag force? Yeah, we talked about drag forces. You should know that drag force is proportional to v squared. Do you need to know the Magnus force? If I gave you an equation like this, you should be able to recognize that it's involved cross products. You should be able to model it up. But now down to the details. Is this equation needed? No, that's very specific. Is a drag equation like this needed? No, that's very, very specific. The idea is you need to be able to implement the physics we talk about in the assignments, the labs, or the tests. I will always give you the physics, as in I will give you a statement of Newton's law. I will give you an expression for the forces acting on objects. Your task is always to take that equation of motion. Here we go. You would be given this. Your task is to be able to take that and turn it into this, oh boy, into that system of equations, and then solve that system of equations using a numerical model. That's what you need to be able to do. Okay. Just looking at the chat, don't see any more questions all the way through here. So that concludes what I want to talk about projectile motion. And I said, this is covered if you want to take a look at the textbook. There's a page and a half if you want to read about such. I'm going to turn the lecture recording off and we'll continue this next time. And then I'm going to dive in talking about the assignments in the lab.